This is example 17. Focus more on condensation of steam on vertical plate. So let's take a look at the question. Saturated steam at atmospheric pressure condensed on 2 meter high and 3 meter wide vertical plate that is maintained at 80 degrees Celsius by circulating cooling water through the other side. So the figure below shows this configuration, and then we have to determine the rate of heat transfer by condensation to the plate, and the second one is the rate at which the condensate drips off the plate at the bottom. So for the first one, for the question number 1A, question A is to determine what is the Q dot. Okay, Q dot for the condensation. And then for the second one, the rate at which the condensate drips off is, we have to determine what is the M dot. Okay, so now we have to take a look at the properties. These properties of water will be referred to the table appendix at the back of your book. We have appendix, and then to refer to the appendix, you have to refer the properties of water at saturation temperature of 100 degrees Celsius for the HFG. So previously I've already told you that we have to determine the HFG and rho V vapor at saturation temperature from the previous video. So the properties of liquid water will be evaluated at film temperature. What we have to do is to add it, or to sum up T saturation and T surface and divide it by 2. So we have T saturation of water is at 100 degrees Celsius. Why? Because saturated steam at atmospheric pressure. So we know that water will be we know that water at 1 atm, the T saturation is 100 degrees Celsius. That's why our T saturation is 100 degrees Celsius, because at 1 atm, T saturation is 100. I believe that all of you understand about the saturation temperature, since the saturated temperature is already been introduced to you in thermodynamics. So then we have to refer to table A9. So we get the T saturation is at 100 degrees Celsius, and then T surface is at 80 degrees Celsius, and divided by 2 we got 90 degrees Celsius, and refer to table A9 for the properties of rho liquid, mu liquid, V liquid, Cp liquid, and K liquid. So before that, we have to determine actually what kinds of information that need to be extracted from the table A9, because we have a different types of equation for different types of regime. So in order for you to solve the problems in condensation, what you have to do, as I mentioned before, what you have to do is to assume that these problems is at the wavy laminar flow, which is the Reynolds number is in between 30 and 1800. So let's take a look at the equation for wavy laminar. So I've already listed out all the equation that will be used in condensation problems. So now we have these two, H star Fg and H star Fg. First H star Fg and second H star Fg. So both of these equations have different conditions. The first one, as I mentioned before in the previous video, this is for the saturated liquid problems. If you have saturated liquid problems in your question, and then you can use the H star Fg. So what is the importance of H star Fg is to find what is the M dot, since Q dot is equal to M dot H star Fg. So the second one here, this is the first one, this is the second one. Second H star Fg is for superheated vapor. The first one, H star Fg for for the liquid, for the saturated liquid, which is below than the T saturation. Okay, your problems is below than T saturation. For the second one is above T saturation here. This is saturated vapor. So now take a look at this question. Is it superheated vapor? No, of course, this is not the superheated vapor problems. Since in the question it's already mentioned that saturated steam, therefore your H star Fg will be used the number 1 equation. Okay, so this is number 1, this is number 2. So your problems here is below than T saturated, therefore you will use H star Fg for number 1. So superheated vapor will not be used for determining the H star Fg. So now we have a laminar wave free. So all of this is the equation to be used for the laminar wave free. Second is laminar wavy flow, where you have to find laminar wave free and wavy laminar and turbulent flow. What you have to do is to determine the Reynolds number first. So after you determine the Reynolds number, then you have to compare either your assumption is in that region or not. So this is equation for laminar wavy flow. Before you can determine the H vertical wavy, you have to substitute all the information for the properties inside this equation to determine the Reynolds number wavy first. And after you determine the Reynolds number wavy, you can substitute into H vertical wavy to determine what is the heat transfer coefficient. So the last equation is turbulent flow, the same as laminar. You have to find what is the Reynolds number, and then the H. After you determine the Reynolds number vertical turbulent, you have to substitute into this equation to find what is the H vertical turbulence. So for the turbulent flow, we know that the Reynolds number must be greater than 1800. For the wavy laminar, it must be in between 30 and 1800. For the laminar wave free, the Reynolds number is in between 0 to 30. So next is incline. So if we have incline problems, so what we have to do here, H vertical, will be using this H vertical from turbulent flow, laminar flow, or laminar wave free. Okay, so after you determine the H vertical, then you can substitute into this equation. But the theta here is the degree of inclination. So next is horizontal tubes and sphere. So for these problems, we do not need to find what is the Reynolds number, since we have only one equation. Then you have to substitute directly into this equation. So what is the difference between horizontal tubes and sphere is this factor 0.2729. This is for the horizontal tubes. In case you want to find what is the H sphere, then you have to substitute or to change this value into 0.815. And then we have another problem where we have to find what is the H for the horizontal end tubes, which means tube banks. So for the H horizontal end tubes, what you have to do is you can directly substitute into this equation, or you want to calculate one by one. So you have to calculate what is the H horizontal tubes from this equation into this. Okay, H horizontal, and then substitute into this equation. For the n here is the number of tubes in the rows. So you have to, from that question, you have to determine what is the number of rows. So now what we have here, to determine the Q dot condensation, we know that we have to find what is the H, AS, and then T saturation minus T S equal to m dot H star FG. So now our first question asks us to find what is a Q dot condensation. Okay, so now we have AS, H. Do we have H here? No, we do not have H. AS, yes, we can determine from the configuration. Okay, the dimensions of this flat plate or the wall vertical plate. Okay, T saturation, we already know what is the value of T saturation. What about TS? We know that the TS value, surface temperature value, where the surface temperature is at 80 degrees Celsius. Now we do not know what is the H here. What about this M dot and H star FG? Can we use this equation? No, of course no, because we cannot determine what is the mass flow rate. Yes, we do know about the H star FG. So the mass flow rate will be determined for the next question, the rate at which the condensate drips off. So our option is only by using this equation. So now we have to determine what is the H value. So H, as we know, we have three different regimes. First is laminar wave free, second is laminar wavy flow and turbulent flow, and the last one is a turbulent flow. So how can we determine? Because each of these equation, each of this regime has different types of equation for the Reynolds number. Now we have to make an assumption. So first assumption must be wavy laminar flow. So what we have to do, assume wavy laminar flow. So when we assume wavy laminar flow, directly use the Reynolds number vertical wavy. So substitute your values, properties values inside this equation. So I will not write down all the equation. I will just put the value of Reynolds number. So the Reynolds number vertical wavy that I get from here is 1287. Okay, please substitute your value inside this equation, because our first assumption is laminar wavy flow. So substitute into this equation and then get what is the value of Reynolds number vertical wavy. So I get from this equation the vertical Reynolds number wavy is 1287, which is this value is in between 30 and 1800. So therefore our assumption is correct. Okay, if you already verify that your assumption is valid, then you can go to the H vertical wavy. So since you already assume wavy flow, wavy laminar flow, and then yes, it is in the wavy laminar flow because you compare the Reynolds number with this range. After you verify, and then please substitute values Reynolds number here into this equation to determine what is the H vertical wavy. So from here, what I get, H vertical wavy is around 5850 watt per meter dot Kelvin. So this is my heat transfer coefficient. Okay, remember, substitute because you already assume that this is laminar wavy, so you only take out these two equations. Okay, if yes, Reynolds number you calculate, yes, your Reynolds number in between 30 and 1800, then go to the H vertical. If not, please assume the next, which is turbulent flow. Okay, now I already verified that my problem here the condensation problem here is in laminar wavy flow from the Reynolds number wave V. So now we already determined the H here. H here, heat transfer coefficient is already determined because we know we already verified that this problem is wavy laminar flow, and we already determined H vertical wavy. So we already have all the information here. So we can calculate AS and T saturation we have, and TS, T surface, also given in the equation. So what we have here, after that, we have to substitute into Q dot equal to H AS T saturation minus TS. So Q dot equal to, our H is 5850. What about the area? Surface area is in rectangular. So this condensation occurs at 3 meter times with 2 meter. So our area is this surface area. So surface area is this. Therefore, our surface area is 3 times our surface area is 3 times 2. 3 times 2, and T saturation is 100 minus 80 is T surface. So where do I get that 80 values? 80 degree value is from here. Vertical plate that is maintained at 80 degrees Celsius. So after that, what we get here is Q is about 7.02 times 10 to the power of 5 watt. So this is we already answered the first question. So the next question here is to find what is the M dot. So we know that the Q dot is equal to M dot times with H star Fg. Now we have to determine what is the H star Fg. So I've already mentioned that H star Fg have two different equations. So now what we have to do is to use the equation number 1, since our problems is below than T saturation. So the first one is below T saturation, number 2 is greater than T saturation. So number 1 is below than T saturation. You have to plug in all the values here from the properties here. Substitute into this equation. So you will get what is the value of HFG. So my H star Fg here, my H star Fg equal to 2314 times 10 to the power of 3 joule per kilogram. So after I get this H star Fg, I will substitute into this equation. You may rearrange this equation. So your M dot is equal to Q dot divided by H Fg. So now from here we will get that the value for the M dot condensation here is 0.303 kilogram per second. So you already answered the second question, the condensation rate. That's all for the example 17.